Hi everyone, I'm Eleanor Chodroff. I'm a lecturer in phonetics and phonology at the University of York, and I'll be presenting Structure and Cross-linguistic phonetic realization. So a primary question in linguistic research is to answer what the range and limits of cross-linguistic variation are. So these are described in many different ways. We might call them linguistic universals, cross-linguistic tendencies, generalizations, but the key thing about these cross-linguistic generalizations is what these reveal about the structure of the grammar, and with a cognitive bent, what do these reveal about the structure of the grammar in the mind of the speaker. So some cross-linguistic generalizations from traditional branches of linguistics might include the following. So in syntax, one of Greenberg's famous universals is when a demonstrative numeral and descriptive adjective precede a noun, they're always found in that order. If they follow, the order is reversed. For morphology, another Greenberg universal, no language has trial number unless it has a dual, and no language has a dual unless it has a plural. And for phonology, it's almost always the case that a language will not have voice stops without also having voiceless stops. So in today's talk, we'll also be concerned with cross-linguistic generalizations, less about what we should call these generalizations, whether they're universals or tendencies, but more about the fact that these cross-linguistic observations reveal constraints on the linguistic grammar. So constraints on syntactic variation, morphological variation, phonological variation, and just in general the structure of linguistic systems. So importantly, the big question now is, what about phonetic variation? What are those constraints? So if we think about phonetic variation, the first thing I think a lot of phoneticians will think of is the variation that is present even just from talker to talker within a single language. So this is a famous figure of American English vowels from 76 talkers. This is from Peterson and Barney, 1952. On the x-axis we have F1 in hertz, and on the y-axis we have F2 in hertz. These are phonetic measures that roughly correspond respectively to the height of a vowel, F1, so we have high vowels and low vowels, and the frontness or backness of a vowel. So back vowels are here, and front vowels have a high F2. And each point here is a pair of talker means for F1 and F2 in this vowel space. Again, these are all American English speakers, a lot of variation across talkers. What we can't observe here is whether there is any structure within these categories, but what we can take away is there definitely is variation from talker to talker. Turning now to variation across dialect, the picture is further complicated. So these are all dialects of English: Australian, London, New Zealand, York, UK, and Newcastle, UK. And here we've now flipped F2 and F1 to better correspond to the articulatory location of the vowel. So we have E in the upper left corner, U in the upper back, and A in the lower part of the vowel space. And even when the phonologies are pretty similar, not identical, but pretty similar, there's still a lot of variation. And are there any generalizations to be drawn from this variation? Well, that remains to be seen. So there has been some research on universals in phonetic variation. Most famously is voice onset time, so VOT. And it's been found that the VOT, which is approximately the duration of a stop consonant, so the VOT of K tends to be longer than the corresponding VOT of P. Within a speaker, within a language, whichever pair of means you're comparing, there tends to be this ordinal relationship. We'll actually be looking at that a little bit more today. Another phonetic universal that seems to be well established is that of intrinsic F0. So the F0, and you can think of this roughly, and this is very rough, as the pitch of a vowel. The F0 of high vowels like E and U tends to be greater than the F0 of low vowels like A. Another universal we might consider is utterance final lengthening. So across languages, as the speaker approaches the end of an utterance, there tends to be a decrease or slowdown in the speaking rate. And there's a great blog from Christian DeCania that sort of goes through several phonetic universals, which ones seem to be pretty well established and which ones might need a little bit more research. So overall, we do have some phonetic universals we might be able to have trust in, but the number of patterns and the number of languages investigated have been limited. Why is this the case? Well, for a while there's simply been insufficient cross-linguistic speech data. So phoneticians might be able to get a hold of a handful of languages, But are we really ready to then claim that this is universal based on, the small sample of languages we were able to obtain? This is in part related to the fact that for a very long time, there's simply been insufficient computational power. Speech, if we're looking at phonetics and specifically speech data, then we're going to be working with audio files, which take up a lot of space on the computer and a lot more than text files. So there's simply the fact of storage on the computer, and then there's the additional part of being able to process those audio files, which require additional skill sets and additional computational power that I think has only recently come into play. So these things are all changing, making it more and more viable for us actually to investigate universals in phonetic variation. So in today's talk, we're going to focus on structure in phonetic variation and related crosstalker and cross-linguistic generalizations. And this will be largely facilitated by large spoken corpora and also corpus phonetics techniques. And hopefully through this analysis, we'll be able to uncover some constraints on the phonetic grammar. So the next part of part 1, I'll be focusing on structured variation and stop voicing in American English actually, but sort of setting the stage for what's to come later on in this talk. So in today's talk, there's going to be a lot of focus on structured variation among speech sounds. Structured variation, that term, is used in a wide variety of ways. What I will mean by this are the systematic relationships among speech sounds that we can observe across talkers or languages. We can then use this structure to identify constraints on phonetic realization. So what I'm going to do first is just lay out the framework I'll be working with, just to indicate what levels of representation I'll be assuming in speech production. So this is a pretty traditional framework. I'm going to be assuming that there is an abstract phonological surface segment that might be composed of the distinctive features of the segment. This surface segment is then phonetically realized into a set of abstract phonetic targets. Okay, these are abstract, but they might indicate the motor plans or possibly even auditory goals of the speaker to realize the phonological surface segment in phonetics. So this process, this mapping from the phonological surface segment to the abstract phonetic targets, is called phonetic realization. The phonetic targets are then physically instantiated via the articulators, which then gives rise to a corresponding acoustic form. And today we'll mostly be working with the acoustic form to sort of then work backwards to understand a little bit more about phonetic realization. So now that we have the framework laid out, let's take a closer look at the process of phonetic realization and how variation might arise in this process across talkers and languages. So on the left-hand side, I have the phonological surface segment of K, and this is represented with a set of distinctive features that specify the place of articulation, voicing, and manner of articulation. And these are then mapped to a set of phonetic targets on the right-hand side, which I've represented with a gestural score. And this indicates what the tongue body should be doing to implement K, how long the constriction should be made, where the constriction should be made, and what the glottis should be doing. So the opening between the vocal folds, should it be spread? If it is spread, how long is it spread? And what's the timing relationship between these gestures or these phonetic targets? Now, what you might notice is that the aspects of the left-hand side absolutely correspond to aspects of the right-hand side, but so these distinctive features, however, do not specify exactly what should be going on in the phonetic targets. So we have a place of articulation feature, but it says nothing about where exactly the constriction should be made and for how long. And the left-hand side indicates, okay, plus spread glottis suggests there should be a glottal spreading feature, but for how long? And how should it be timed relative to the constriction? This is all going to be part of the phonetic realization process. And the important part is that this underspecification here allows for some variability and in the phonetic realization across talkers and languages, or it could. So we're going to be looking at this process a little bit more, but we can't look at the phonetic targets exactly. We can only look at the physical correlates of those, like the physical output of those phonetic targets. we'll be working with the acoustic output, and one reasonable acoustic instantiation of, say, glottal spreading, one of the assumed phonetic targets, is voice onset time, VOT. And again, this is the duration from the stop release, so when the tongue body is released, to the onset of voicing, okay? So when the glottal spreading gesture ends. If we look at variation in this acoustic instantiation of glottal spreading across talkers of a single language and dialect, American English, we see that there is actually a lot of variation in this acoustic output. So this is the mean VOT, a histogram of the mean VOT from 180 speakers of American English. This is from the Mixer 6 corpus of read speech. And we can see that in this distribution, the mean is 56 milliseconds, but the range is pretty considerable. Some speakers have a mean VOT for K that's less than 40 milliseconds. Others are closer to 80 milliseconds. When we turn to the other aspirated stop consonants of American English, that variation is just replicated. So we see for the mean VOTs of P, some speakers are down at almost 20 milliseconds, whereas others are up at 80 milliseconds. And for the implementation, the realization of T, we can see some speakers have a mean VOT of 40, others are almost up at 100. So there's a lot of variation in the phonetic realization of these stop consonants, which gives rise to variation in the actual acoustic instantiation. Now, one hypothetical scenario is that there's independence in the phonetic realization of phonological segments. So speakers can sort of choose how they want to control the phonetic targets underlying VOT for each of the stops independently. So one talker could have targets that give rise to a mean VOT of 40 milliseconds for P, 90 for T, 50 for K, and another talker could have a completely different pattern. If that were the case, so if the talker mean VOTs for P, T, and K are independent of one another, what we should see is basically no correlation between pairs of talker means within a laryngeal, between the places of articulation. So here we have the marginal histograms represent the range of talker means for a given stop consonant, like P here on the x-axis, T on the y-axis here, and each point is a pair of talker-specific mean VOTs. And so if there's complete independence in this mapping from surface segment to phonetic targets, we would expect a picture like this. The actual scenario looks more like this, where we actually observe strong covariation among place of articulation and across talkers. So talker mean VOTs for P, T, and K are strongly correlated with one another. They are not independent. Okay, and we can see the correlations range from about 0.77 to 0.83, and this is connected speech. So what does this mean for the process of phonetic realization? So this structure in the acoustic output, the VOT, indicates that there's some sort of structure in the input. So there's something yoking together the phonetic realizations of P, T, and K so that they are not wholly independent of each other. In fact, they're pretty correlated with one another. So in the next section, we're going to explore this covariation and what gives rise to this covariation a little bit more.